take a look at some review questions for Chapter 1, the Copernican Revolution. Question number 1. Mars, Jupiter, and Saturn show retrograde motion because, well, we're using the actual reason why they show this loop-back behavior. As you study this behavior over the course of months, you would see that Mars appears to be going in this direction, then it loops back and goes back in this direction. That is the end result of the fact that these planets, being outer planets to the Earth, are moving slower than the Earth is. Earth is overtaking them, and by Earth's perspective, looking at the stars in this way, that perspective changes as Earth moves faster past them in its orbit. So we see this retrograde motion because Earth moves faster in its orbit than the outer planets. Question 2. How did the geocentric model account for the day and night on Earth? Now the geocentric model, geo mean Earth, and centric mean Earth-centered. So in this model, that was Ptolemy's or Aristotle's model, that the Earth was the center of all things. And so how do you account for day and night on the Earth? Well, day occurs when the sun on the celestial sphere actually reaches your sky and then sets as the celestial sphere moves. So we count for day and night in the geocentric model because the sun is orbiting the Earth. Question 3. Epicycles were used in Ptolemy's model to explain, well, we had this problem with the loop-back behavior. You know, if you use Ptolemy's model and the sky is moving on its own, we had these wanderers, which were planets, moving in their own accord across this celestial sphere. So they had their own definite paths called deferents, but every once in a while they would loop back and then continue on their way. And how do you explain that behavior if the Earth is the center of the solar system? You explain it by adding these little loops, which were called epicycles. So epicycles were used to explain why retrograde motion occurred. Question 4. The geocentric model was supported by Aristotle because, well, Ptolemy had proposed this model that the Earth is the center of the solar system, and the sun and the planets and everything else went around the Earth. This was supported by the greatest scientist of the day, Aristotle, because, well, he looked for parallax. I mean, if this is true, if the Earth were actually going around the sun, you should see parallax between objects that are closer to you and objects that are further away. And Aristotle could not see that parallax. So that was one thing. Of course, the parallax was too small for human measurement in those days. Another thing is we don't feel as if the Earth is moving. And so this is a good reason, because if the Earth were going around the sun, you would expect it must be moving at incredible speeds, and it is. It's moving at 30,000 meters per second, 30 kilometers per second in its path around the sun. And we don't feel that. And the reason we don't feel that is because everything with us is moving at the same speed. So it's a relative thing. If everything is moving at the same speed, you might as well think that you're at rest. Also, objects fall towards the Earth, not the sun. Why does this happen? Well, Earth is in closer proximity than the sun, so gravity is more of an effect on objects near the Earth. D, we don't see enormous wind. That's because, again, everything's moving together, so we don't see enormous wind. So all these reasons would be valid reasons. If you didn't think about the problem long enough or had more information, these would be valid reasons to support the geocentric model, and they were all used by Aristotle. Question number 5. The heliocentric model assumes, helio meaning sun, centric means centered. So the sun-centered model, heliocentric, assumes, and looking for the answer in there, the sun is the center of the solar system. That's what it assumes. Question number 6. Copernicus's important contribution to astronomy was, well, as we discussed, Copernicus proposed the heliocentric model, the sun-centered model of the solar system, where the planets went around the sun in more or less circular orbits. So his contribution was to propose a simpler model for the motion of the planets in the solar system, because this model didn't have as many epicycles. It didn't have these epicycle upon epicycle problem. It just had a small epicycle because he assumed that the orbits were circular and not elliptical. In fact, question number 7 says Copernicus's heliocentric model was flawed, slightly flawed, because he assumed the planets moved in circles around the sun, where actually the sun and the planets move around their own common center of mass, and the net effect is that the planets seem to move in an elliptical orbit about the sun, where actually the sun is just kind of wobbling around as the planets are moving around, and the net effect is an ellipse. So he had to keep small epicycles to account for small changes, but it was really very, very minute correction. Question 8. Who published the first astronomical observations made with a telescope? Telescope invented in 1604, used within years after that by Galileo, who observed many things, the moon's going around Jupiter, the mountains on the moon and the mare on the moon, sunspots, the phases of Venus, all these things observed by Galileo, and he published them very quickly in 1610 in what was called the Starry Messenger, detailed all these observations in that publication. Question 9. Which of Galileo's initial observations was most challenging to establish geocentric beliefs? Well, if you're going to go geocentric, you've got to go all the way. So you're saying that the Earth is the center of all motion and everything's going around the Earth. So if you're going to challenge that, what would be most challenging is the fact that if you observed over the course of day after day after day, you would see that there were satellites going around Jupiter, 4 now called Galilean satellites, 4 major moons going around Jupiter, and that would pretty much put holes in the theory of the geocentric model. Here's Galileo plotting those satellites over the course of days, and you can see them moving around Jupiter, and you can see this with just a nice basic telescope. You can look at Jupiter and see these moons traveling around it from day to day. Question 10. Which hero of the Renaissance postulated 3 laws of planetary motion? The 3 laws of planetary motion, based on the data of Tycho Brahe, were developed by his apprentice, Johannes Kepler. And then Isaac Newton used that empirical data, that just rough data, those rough results, to help him formulate his 3 laws of motion and his gravitational law. So it was Kepler who came up with these empirical laws of planetary motion. Question 11. Kepler's first law of planetary orbit states that, well, his improvement over Copernicus's model was that the orbits were elliptical in shape. So his first law states that the orbits of the planets go around the sun. They are non-circular. They're indeed elliptical in shape. And so all this is stated in his first law. Question 12. The Earth is closer to the Sun in January. From this fact, Kepler's second law tells us, well, if the Earth is moving in an elliptical orbit from the first law, and if it's closer, that means, and sweeps out more area in equal amounts of time, it must be doing it faster when it's closer to the Sun, because the pi is wider, the pi of area is wider in that instance. So the Earth is moving faster in January than it is in July. Kepler's third law relates a planet's distance from the Sun and its orbital. This is question number 13. Well, the third law relates the time it takes for a planet to go around the Sun to its distance from the Sun. So it relates its planet's distance from the Sun to its orbital period. And in fact, the period of time squared is related to the distance from the Sun cubed. Question number 14. Newton's law of gravity states that the force between two objects, well, it drops off as the distance squared, so it's inversely proportional to the distance squared. I don't see that answer there, but it is proportional to either mass involved. So if one mass increases, the force increases proportionally. And if the other mass increases, the force increases proportionally. So it's proportional to either mass involved with the gravity. So the force between two objects increases with mass. That concludes your quick quiz on Chapter 1, Copernicus's Universe.